Okay, everyone. Today's lecture is Chapter 9, One Sample Hypothesis Test. Okay. So this chapter is, as I told you before, this chapter is most important chapter in this course. So all the students should know this hypothesis test. So the reason why you study the stochastic is for this chapter. So in this hypothesis test, we will study the research methodology. So all the researches are have a step, and if you have one idea, so then if you have one idea, then you have to formulate this idea to the hypothesis, and then gathering the data and do the statistic test and make decision this hypothesis is correct or not, and revise your idea and so continue this process. So that is the research. So you have to study the hypothesis test, and you have to do the hypothesis test again and again and again in every research topic. Okay, so okay, what is the example? So of course you have to use the hypothesis test. So the hypothesis test has these 5 steps. First, state the hypothesis to be tested, and step 2, specify what level of inconsistency, and step 3 is collect data and calculate necessary statistic test. And so the step 2 is that so decision rule, we have to define the decision rule. We will study this step again later. And the step 3 is to collect data and calculate the necessary statistic to test the hypothesis and make a decision. Okay, our hypothesis is accepted or failed to rejected or failed to rejected or something like that. And then if we get a result, get a conclusion, then we have to react based on this conclusion. So first, we have to state the hypothesis. Okay? So good hypothesis. So you have to define very meaningful hypothesis. We say that this hypothesis is null hypothesis. Null is the null comes from German, and null means 0. So it is null hypothesis. And if you define the null hypothesis, then you can define the alternative hypothesis. So null hypothesis should have alternative hypothesis. So if this null hypothesis is true, then this alternative hypothesis should be false. And null hypothesis is false, then alternative hypothesis should be true. True, then false, false, then true. So it is impossible both of them is true or both of them is false is impossible. This kind of thing is impossible. So when you define the null hypothesis, you should be able to define the alternative hypothesis which has this property. Okay. Of course, null hypothesis must be stated a precise way, so it should not be vague or redundant. Okay, and it is more philosophical area. So if a null hypothesis happen, yeah, so then expect reject or something like that. Read it. If we reject null hypothesis, then alternative hypothesis is the case. Okay, so if we reject the null hypothesis, then alternative hypothesis should not be rejected. And alternative hypothesis is rejected, then null hypothesis is not rejected, then alternative hypothesis should be rejected. So these two statements should be complement. For example, the null hypothesis is that so dependent is innocent, and alternative hypothesis is that dependent is guilty. So if it is the null hypothesis is accepted, then alternative hypothesis is failed to accept. And alternative hypothesis failed to accept, then so this guy is not guilty, is guilty. So then, so these two statements is complement. So if it is true, then it is false. If it is false, then it is true. So it is impossible to both of them is true and both of them is false. So it is not possible in statistics. So, and drug testing, no illegal steroid use in the Olympic game. If Usain Bolt get the gold medal, after then he should go to the nursing office or clinic and should check the steroid abuse. Okay, so then no illegal steroid use, then that is null hypothesis. Illegal steroid use is alternative hypothesis. So these two statements should be complement. If this one is true or rejected, it is false or rejected, then it should be true or not rejected, and vice versa. So if you have some fingerprint, if you use the iPhone, then you can, iPhone or in these days all the cell phone has the function to check your fingerprint, or some the IT machines has the password system. So if you are authorized, so you are accepted by this automatic authorization machine, then you can use the phone or machine. Or if you reject it, then you cannot use the machine. So in this case, it is a null hypothesis and alternative hypothesis. Okay, step 2 is specify the decision rule. So we use before collecting the data, the researchers must specify that how the event will be used to reach a decision about the null hypothesis. So our legal system, the evidence presented by the prosecutor must convince a jury beyond reasonable doubt, okay, that the defendant is not innocent. So in steroid testing, the lab that analyze the urine or blood sample must construct the test to decide whether the sample exceeds the agreed upon the benchmark or threshold. So biometric screening also, so the designer of the security system determined that how many discrepancies of the fingerprint would indicate the unauthorized user. So that is the decision rule. After we have the decision rule, so the step 2, 3, and 4 is data collecting and decision making. So we collect the data from many methods, and then apply the decision rule, and then make a decision. After the make a decision means that we accept the null hypothesis, so reject the null hypothesis or not reject the null hypothesis. That is the decision making based on the collected data. And if the null hypothesis is rejected or accepted, then we take the action based on the result. So it is very philosophical problem that can the null hypothesis be proved? It is impossible. We just reject or accept the null hypothesis. That does not mean that truth. Okay? Based on the collected data, the null hypothesis can be not rejected, but that is not means that the null hypothesis is true. Okay? If we fail to reject null hypothesis, then so it is based on the data we collected. Okay? So if we find some special data, so today, then the once null hypothesis was not rejected, but today, if you have new data, then you can reject the null hypothesis. For example, null hypothesis is that there is no black swan. So every swans are white. So it was not rejected. This null hypothesis was not rejected until the 18th century or 19th century. But once one explorer found one black swan in I don't know where it found it, Australia or something like that. So then this null hypothesis was not rejected, but today, once the black swan is observed, then this null hypothesis it can be rejected. So even the Einstein's theory is until today, it is not rejected until today, but many scientists still think that Einstein's theories are wrong. So we don't have enough data to verify that Einstein's theories are so wrong, so not rejected. Okay. So anyway, we are not finding truth. We just assume the null hypothesis and check the data that this null hypothesis is supported or not. So this null hypothesis is rejected or not rejected based on the collecting data. So anyway, that's why we can consider that two types of error. One is that we assume that null hypothesis. We don't know the truth of null hypothesis. So this null hypothesis can be true or it can be false. But based on the collected data, we can reject the null hypothesis or fail to reject the null hypothesis. If null hypothesis is true, and if we fail to reject, so then it is correct decision. If the null hypothesis is false, and based on the data we reject the null hypothesis, then it is correct decision. So it has no problem. These two cases has no problem. But the problem is that null hypothesis is true, but based on the data collection and the stochastic method, we reject the null hypothesis. Then it is an error. For example, null hypothesis is that there is no black swan in this universe. But once you found a black swan, then so you didn't based on your data you didn't find any black swan. Then you may say that this null hypothesis first, but you may have some this one. So fail to reject this null hypothesis, then you may have this error. So if the null hypothesis is true, but if you reject this null hypothesis, then you have the type 1 error. If null hypothesis is false, but if you fail to reject this null hypothesis, then you have the type 2 error. Okay? Because so rejecting the null hypothesis when it is true, then we say that it is type 1 error. Failure to reject the null hypothesis when it is false is a type 2 error. Okay. So the probability that we have type 1 error is denoted alpha, and the probability that we have type 2 error is denoted beta. So type 1 error is that reject the truth hypothesis, and we symbol it by alpha. Okay? So this alpha is that probability that we reject the null hypothesis under the null hypothesis is true. So it is type 1 error. Another name of type 1 error is false positive. Another name of type 2 error is false negative. Okay? We've studied this word false negative, false positive, and false negative when we studied conditional probability. Bayes theorem. When we study the Bayes theorem, we consider that so false positive and false negative. That is type 2 error, fail to reject a false hypothesis. So we denote that beta. So 1 minus beta is the correctly reject the false hypothesis. So 1 minus beta is so correctly reject a false hypothesis. It is called power. So this prediction power. Okay? And of course, the type 2 error probability of type 2 error is given by beta. Probability that we fail to reject null hypothesis under the condition that the null hypothesis is false. Okay? So and power is that reject null hypothesis under the condition that null hypothesis is false. It is good news. It is good news. But these two cases are bad news. Okay. Okay. So we say that power is 1 minus beta. So if we desire to test that avoid a false negative, so small beta. So, but we also want to avoid the false positive, small alpha. So alpha and beta. So alpha and beta are both of them are not good news. They are all bad news. The smaller probability of beta and the smaller probability of alpha, so is better. But unfortunately, if the sample size is fixed, if you collect the data and the size of sample is fixed, so then we have a trade-off between alpha and beta. That means if the sample size is fixed, then alpha is increasing, then beta is decreasing, and alpha is decreasing, then beta is increasing. Okay. So we cannot alpha and beta, both of them should be goes down. That is what we want. But it is impossible if the sample size is fixed. If you're gathering 100 samples and if these 100 samples are not changed, so the number of samples are not changed, then it is impossible. So alpha is up, then beta down. Alpha down, then beta up, and vice versa. Beta down, alpha up, beta up, then alpha down. Okay. So if your household household carbon monoxide detector's sensitivity, this threshold has some threshold. So this sensitivity is increased to reduce the risk of the overlooking danger. So then you would like to reduce the risk of the overlooking danger. So then that means reduce beta. So then at the same time, you may have many false alarms. So that means increase alpha. Okay? So they have alpha and beta has the threshold. A doctor who is conservative about admitting the patient with the symptom of the heart attack, so then he is very conservative. So if he found small evidence to get a heart attack, heart attack, then so he send the patient to ICU. So then that means this doctor would like to reduce beta. But if so, then it admit more patient with no heart attack. Okay? So the ICU will be filled by some suspicious patient. So then it is so increase alpha. So, and so on. So alpha and beta cannot reduce together. Alpha is reduced, then beta is increasing and increased, and alpha is increased, then beta is reduced, or something like that. So both alpha and beta can be reduced when, if you want to reduce alpha and beta simultaneously, only by increasing the sample size. Sample size is increasing, then alpha and beta can be reduced together. So the sampling is very important. That's why we have to study the statistics. So sample size, if you increase the sample size, then you can so reduce the probability alpha and beta. Okay, statistic hypothesis test. So we will do the statistical hypothesis. Statistical hypothesis. So statistical hypothesis is the statement about the value of population parameter that we are interested in. For example, so mean or proportion or variance. But in this course, we will study only the case of mean. So our hypothesis only depends on the mean value. So proportion of our variance is the same as, we can use the same approach as we do for mean. Okay. So for example, so you need some threshold, the benchmark. So you'd like to estimate the true value of population mean. True value of population mean. We don't know what is the true value of population mean, but let's assume that true value of population mean is 5. And the sample mean should not differ greatly from 5. So here is sample mean mu 5, then the population mean mu is 5, then sample mean is around this interval. We've studied the confidence interval. Okay. So we will the statistical hypothesis, statistical null hypothesis for the mu is based on the benchmark value. So mu zero is our benchmark value. So hypothesized value mu zero, it does not come from the sample. But it is based on the past performance or industrial standard or target value or product specification. Okay. So the let's study the example later. So for a mean, our null hypothesis H0 states based on the value benchmark value mu 0. And here is the example. So null hypothesis can be defined like this. null hypothesis is that the population mean is exactly same as benchmark mean. So that is null hypothesis. Alternative hypothesis is that population mean is not same as benchmark mean. Okay, that is alternative hypothesis. Okay, if null hypothesis is true, not rejected, then alternative hypothesis is rejected. Null hypothesis is rejected, then alternative hypothesis is not rejected. Or, so in this case we say that it is two-tailed test. Two-tailed test. Or we can define the left-tailed test and right-tailed test like this. Null hypothesis is that population mean is larger than our benchmark value. Then that is called left-tailed test. Right-tailed test is that population mean is less than or equal to the benchmark value. So this null hypothesis is the null hypothesis for the right-tailed test. Alternative hypothesis for the left-tailed test is that, so it should be opposite. The direction is opposite. It is mu is greater than or equal to mu 0, but alternative hypothesis says that mu is strictly less than mu 0. And here is right-tailed test alternative hypothesis. So right-tailed test null hypothesis says that mu population mean mu is less than or equal to the benchmark value, and this alternative hypothesis is that population mean is strictly greater than the benchmark value, our mark, so standard value. Okay. So be careful. So let's tailed test, two-tailed test, and right-tailed test. For example, so EPA, Environmental Protection Agency, guidelines for the maximum safe level of radon in a home is 4.0 pci per liter. So then our null hypothesis, so this value 4.0 is our benchmark value. So it is not comes from the data, but it comes from the safety level. If this radon level is larger than 4.0, then it will be dangerous. So that is our benchmark value, mu 0. Okay. And one homeowner so would be concerned if the average radon level is too high. So in this case, homeowner would choose a right-tailed test. Okay. So our null hypothesis is that the radon level, so it's the mean radon level is less than 4.0 psi per liter. And the alternative hypothesis is that mu is greater than 4.0. So it is benchmark value, and it is population mean, which is not given. Okay. So we have a right-tailed test. It is null hypothesis and alternative hypothesis. Okay. And another example is that diode platinum automobile battery has a claimed CCA called cracking amperes of 880 amperes. So then consumer testing agency choose the sample of the several batteries. So and find the average CCA for the batteries tested. So customer testing agency would only be concerned if the battery deliver less than the claimed CCA. The claimed CCA is 880 amperes, 880 amperes. Okay. If this value is larger than their claim, then that has no problem. But it is less than 880, then it may take some problem. So in this case, the null hypothesis is that so the mean ampere of diamond platinum battery is greater than 880 CCA. That is our null hypothesis. Alternative hypothesis is that mu is less than 880. So this 880 is called benchmark, and we say that it is mu 0 benchmark value. And our population mean should be greater than benchmark value. Otherwise, we reject this null hypothesis, and that is bad news. In this case, we use the left-tailed test. And one standard size copier paper should be 216 millimeters, so 8.5 inches. If this width is not correct, then the copy machine makes some trouble, paper jam or something like that. Okay, so this 216 is our benchmark value. So the width should be around 216. It should not be less than 216, and it should not be greater than 216. So our null hypothesis is that the mean of paper width is 216 millimeter. Okay? So this mean mu is unknown population mean for the width of copy paper, and 216 is mu 0, which is benchmark value. So this one is mu should be same as 216. If mu is greater than 216 or less than 216, then it is bad news. So that is alternative hypothesis. If the null hypothesis is rejected, then we have to change the machine or repair the machine or increase the accuracy of the manufacturer process. Okay. So when performing the statistical hypothesis test, we need a decision rule. So now we have the null hypothesis and alternative hypothesis for the left tail test, right tail test, and two-tailed test. So then how can we reject the null hypothesis or not reject the null hypothesis? So in this case, we use the extreme values. So our decision rule is specified by defining the extreme outcome. Okay. So that means here is critical value. We assume that here is benchmark return. It is benchmark value. Here is benchmark value, and here is benchmark value. So we are considering that so mean, population mean, so should be same as mu 0. But so we don't have the value of population. So we may calculate sample mean. We collect the data and calculate sample mean, and we believe that this sample mean is represent the population mean. So this sample mean is around somewhere around population mean. So here, somewhere around population mean, we have sample mean, as we studied in the confidence interval. But if this population sample mean is located in this extreme area, after you gathering the data and your sample mean is in this here or here, far from the benchmark value. So your sample mean is located in alpha over 2 probability area left-tailed, or alpha over 2 probability area right-tailed. So then the probability that our sample mean is far from our benchmark is alpha. So if this sample mean value is located in this left tail or right tail, so then it is so extreme, it is so far from the benchmark mean, so we cannot say that mu 0 and population mean is the same, because this sample mean is located in very extreme probability area. Okay? For the same reason, if the sample mean is located in this area, left-tailed area, and the size of this area, probability that x bar is located in this area is alpha. And this alpha is very small. Alpha is 5% or 1%. So then the probability that sample mean is located in this extreme area is 5% or 1%. So then this kind of event may happen once every 100 times or 5 every 100 times. So that is very extreme case. In this case, we cannot say that mu is greater than mu 0. Okay? Mu is population mean, and x bar is representative of mu. So we would like to say that mu is greater than mu 0. Mu is greater than mu 0. Some mu is here, or so somewhere in here. But our sample mean is less than mu 0, and the distance is too far. And the probability that x bar is located in here, x bar can be located everywhere, but there is all probabilities. But the probability that x bar is located in this area is less than 5% or less than 1%. Then that means this event may happen 5% low probability or 1% low probability. In this case, we cannot say that mu is greater than mu 0. It is the same. X bar is located in here, then we cannot say that mu is less than mu 0. because we observe very extreme event. Okay. So if the sample mean is too much far from the benchmark value, differ from benchmark value, extremely different from the benchmark value, then we just reject the null hypothesis. We might reject the null hypothesis if the sample mean is differ from mu 0. Okay? Of course, we have to consider that the confidence level or significance level. Okay? So the decision maker should specify the value of alpha. So this alpha is the probability. So it is the probability that we have type 1 error. So type 1 error, probability of type 1 error is alpha. So we decide the level of alpha by 10%, 5%, or 1%. Okay. Level of, and they say that that is the level of significance. Level of significance. So it is alpha. Okay. So if we specify the decision rule on alpha is 5%, then that means the type 1 error, we may have a type 1 error about 5 times in 100 samples. Okay? So in two-tailed test, the risk spread, so left tail and right tail, so we have to use that alpha over 2. So alpha over 2 for the left tail, alpha over 2 for the right tail. Okay. So our level of significance is 10%, then alpha over 2 is 5% each tail. So left tail 5%, right tail 5%. If we choose the small alpha, then it is harder to reject the null hypothesis. That means if we select a small alpha, then the probability that we may have type 2 error is increasing. Okay. And if we choose the large alpha, then it is easy to reject the null hypothesis. So that means we may have the type 2. So, okay, so then type 2 error, the probability of type 2 error is decreasing. Okay. So how can we select alpha? So alpha is 10% or 5% or 1% or sometimes extreme case 0.1% or something like that. So then what is the best alpha? So nobody knows. So it depends on the situation, but so in many cases 5% level of significance is most popular so level of significance in general. But in finance, risk management in finance, many people use the 1% significance level. So it depends on the studying area, research area. Okay, but so 5% is good. In many cases, people use 5% significance level. Yeah. Decision rule. So for example, suppose the sample mean in the Bladon test is far enough above 4.0, far enough from 4.0, then we reject the null hypothesis that so this one, and so we cannot reject the alternative hypothesis. The same sample would also permit the reject of any value of mu less than mu is 4.0, so that actually we can reject this null hypothesis. Okay, so read other pages, and let me stop here, and I will continue the more so detailed null hypothesis test next lecture. So we still have 2 lectures for the chapter 9. Thank you so much, and see you next lecture.